So let's look at Rutherford's planetary orbit model. So there are a lot of good things about this model, but it's not a correct model. We got to understand that. But it gives us a good sense, a much better sense of the atom than the plum pudding model. And we will get to the quantum mechanical model in a second, or in a day or two. So let's just look. So Rutherford's concept is that you've got a heavy nucleus and the electrons are orbiting that nucleus. So we can say, call the heavy nucleus M and the mass and the electron E, and they each have mass. And because of the heavy nucleus, the electron orbits it. It's like the fact that the Earth orbits the sun doesn't orbit the Earth. And actually, you got to keep, you probably are aware, but you may not be, that they do actually each orbit each other a little bit, but you have to look for the center of mass. What they orbit is the center of mass. And if the center of mass is right here, for example, then the nucleus will orbit the center of mass and do a little bit of a wiggle, whereas the electron will orbit the center of mass and do a much bigger movement, right? And so this is actually the concept that we use when we look for one of the concepts that we use when we look for what are they called? Exoplanets? Planets going around other stars. We look for the star's movement, the star's extra little wiggle. That's why I called it a wiggle, because if something's orbiting it, it is also orbiting the center of mass of the system. And actually, when you look at I'm not 100% sure, we're going to calculate it later for the nucleus, but when you look at the sun and the Earth, right, here's the sun and here's the Earth, it's not to scale. The center of mass of the sun and the Earth are somewhere within the sun, right? So the sun does orbit, right? So the center of mass of the system is there, whereas the center of mass of the sun is here. And so the center of mass of the sun does go around that, hence the wiggle, right? Because at some point the sun is going to be in this position, and at some point it's going to be in this position, at some point it's going to be in this position, right? So the sun has this little wiggle to it due to the fact that the Earth and the other planets in the solar system are orbiting it. Again, what you need to understand is with orbits is that the things orbit not each other, but the center of mass of the system. So, if it's heavy enough, then the center of mass is very close to the center of the heavier mass. And so we don't have to worry about the movement of the heavier mass, and we approximate that it is sitting still and the other things orbit it. So let's just take the hydrogen atom to start with. Hydrogen atom. The hydrogen atom has a single proton and single electron. The nucleus has a single proton, and it's got a single electron orbiting. Let's just take that. Okay. What makes the electron orbit the hydrogen atom? Right, of course, it's the electric force. The electric force is equal to K Q1 Q2, and I'll get it right this time, over R squared, R hat, and the electric force for I was just making sure the sign was right? If the two charges are positive, the electric force is radially outward, so this is correct in the radial direction. So let's go ahead and realize that it's an attractive force rather than a repulsive force, because one is positive and one negative charge. And so therefore we know that for the hydrogen atom, you've got K Q1 is Z1E and Q2 is just E, the nucleus and the electron, minus E, over R squared, however far apart they are in the R hat direction, and it's this minus sign that tells you that it's an attractive force. To apply Newton's second law to that and say, okay, so therefore the magnitude of the force KQ1, be careful about the signs to make sure that we recognize how to do this problem. Let's just go ahead and say that the electric force points in the inward direction on the electron, and it has a magnitude of So I've gone ahead and plugged in the charges. It's got a magnitude of, because z is 1, k e squared over r squared, where r is the radius here. And that's r. And it's got a direction in the direction shown. And if we then apply Newton's second law, we would say, it's accelerating in that direction, so we're going to call that the plus x direction. And we would say, therefore, if we apply Newton's second law, plus k e squared over r squared, that force is in the plus x direction, equals ma, but a is the centripetal acceleration, so it equals mv squared over r, because it's going in a circle. So this is Newton's second law applied to the hydrogen atom. I didn't actually ask any questions. I just said we're going to analyze Rutherford's planetary orbit model, and that's one result that we get. We could, for example, say, okay, so how fast must the electron be moving? Well, we know it was Avogadro who approximated that the radius of the hydrogen atom was about 10 to the minus 10 meters, and so therefore we could approximate the speed of the electron in the hydrogen atom. V equals, these two r's are the same, these two r's are the same, it's just the radius, and just make sure we know that we're talking centripetal acceleration. Anything going in a circle has an acceleration v squared over r, speed squared over r. That's what we used for the acceleration in Newton's second law. Okay, back to speed is equal to k e squared over r over mr. That's solving for v, square root, where k, remember, is the constant for in Coulomb's law, 1 over 4 pi epsilon 0. E is the charge of the electron. M is what mass in this case? We were doing Newton's second law applied to the mass of the electron, so I was not being careful. This is the mass of the electron, this is the mass of the electron, and that's the radius of the hydrogen atom, 10 to the minus 10 meters. So then we can go ahead and plug in. Therefore, V equals, and I guess we didn't need to know K is 1 over 4 pi epsilon 0 because it is in the MKS units, 9 times 10 to the 9th. I'm going to stick with MKS units here, 1.6 times 10 to the minus 19th coulombs, and over the mass of the electron, which is 9.1 times 10 to the minus 31, I believe. So you get V equals 1.5 times 10 to the 6. Notice that's not really relativistic because it's a good factor of 200, smaller than speed of light, but it's pretty close. Relativistic effects might take place a little bit. We might have to take into account, but it's only a very small fraction of the speed of light. Let's also ask, what is the acceleration? Acceleration v squared over r. So the acceleration of the electron is, unless I made an error, it's a pretty large acceleration. And hence, right, this is one of the problems with the model, the Rutherford planetary orbit model, which is that the electron, which is a charged particle accelerating at such a high rate, it would be radiating electromagnetic energy because of its acceleration, but it would radiate it so quickly that it would lose all of its energy and crash right into the nucleus and stop. But we know that atoms don't do that, so the planetary orbit model has a problem. But anyway, let's go on and continue to look at the energy of the electron. So from an energy point of view, we can ask, what is the total mechanical energy, right? The total mechanical energy is the kinetic energy plus the potential energy, and the kinetic energy is 1/2 mass of the electron, v squared, right? So that's the energy of the electron orbiting the nucleus, and the potential energy is minus k e squared over r. It's bound, right? The potential energy, or the electric potential energy, is negative k e squared over r. Or I guess I should say, as an aside, the electric potential energy is minus k q over r. Sorry, I should say that it's got a positive potential energy, but when we plug in the charge of the electron, which is going to be K times ZE, which is the charge of the nucleus, times the charge of the electron minus E over R, and so that ends up being K minus K E squared over R. Okay, let me just address this sign of the potential energy. The sign of the potential energy, imagine that you have two positive charges. Imagine that you have two positive charges. What does it mean to have a positive potential energy? It means that if you have a positive potential energy, it means it's got, if you pin one charge down and you let go of the other charge has potential to get kinetic energy. And indeed, it does have potential to get kinetic energy, and it'll just go away and get more and more kinetic energy. The fact that it has negative potential energy is because it's bound to the nucleus. It's because if you let go of the negative charge, it's not going to go away and get more and more kinetic energy. It will get more kinetic energy, but it's going to move towards the nucleus and stop. It's got, and I guess another way to look at it is potential energy is the electric potential energy, or gravitational potential energy actually, is defined relative to... The potential energy is negative because it's a bound potential energy. The way we calculate potential energy is work is equal to minus the change in potential energy, and work is the integral of F dot dr, where F is what we have on this previous page. And we have to calculate the potential energy. We say that in order to get our limits, we go from infinity to R. And so we say that U at infinity equals 0. So this is how we calculate, this is the definition of potential energy. For any potential energy, but for the electric potential energy, this is what we define. We define our 0 at infinity. Different than when we define our potential energy near the surface of the Earth, we define our potential energy equals 0 at the ground. For a 1 over r squared force, we're always going to define the potential energy equals 0 at infinity. And so, therefore, what you will find is, from that result, you will find this. Okay, moving on. Ahead and write the energy on another page. Just rewriting the total mechanical energy, and then reminding you that, that's just reminding you, it's not therefore, V squared equals KE squared over MR from Newton's second law. We can go ahead and plug that in here, and we find that the total mechanical energy is minus KE squared over 2R. And actually, whatever I said before, this is what tells us, this minus sign is what tells us that this is a bound state. If your total mechanical energy is negative, you are bound. So for example, if you're stuck in a hole, just imagine gravitational potential energy. If you're stuck in a hole and you can't get out of the hole, your total mechanical energy must be 0, which must be negative, right? If you define potential energy at the ground above you, and so you lose potential energy as you get into that hole, so your potential energy gets negative, and if you don't get enough kinetic energy to get out of the hole, then your total mechanical energy is always going to be negative. I don't know if that made sense. A picture might help, right? If we stuck in a hole and our potential energy is therefore going to be negative if we define U equals 0 at the ground. And in order to get out of this hole, the only way we can do so is to give ourselves enough kinetic energy such that the kinetic energy is greater than our potential energy at the ground. And that would give us a total mechanical energy that's positive. But if the kinetic energy is, if K is less than U, therefore E is less than 0, and we're stuck in the hole. Okay, that's what it means to have a bound state energy. We're stuck. And in this case, the electron is bound to the nucleus. And the only way we can get the electron out of the nucleus, we can. How do we do that? We give it additional kinetic energy, right? We give it more energy to rip it out of the nucleus. Okay, so anyway, the total mechanical energy of the electron in orbit around the nucleus is minus KE squared over 2R. Problem number 1 is electrons should be continuously radiating energy because it's and I've said this 3 times, it's a charged particle that's accelerating, and that's what they do. And as it radiates the energy, it should slow and it would emit a continuous range. Instead, we see line spectra, so this goes against the concept of line spectra. And then second, which is a result of that, the electron should crash and burn. Right? It should crash, should lose all its energy eventually and crash into the nucleus, but it doesn't. We know it doesn't because and it should do that in in a nanosecond. It should do it in no time at all because that acceleration is so high. And how do we know it doesn't? We know it doesn't because atoms continue to emit line spectra. They continue to emit radiation. So those electrons must be continuing to emit energy. So now we have to explain how it is the electrons can emit energy without losing it all, and atoms always collapsing in on themselves. So that's all we're going to talk about with the Rutherford planetary orbit model, and we will move on to applying some of what we know about quantum mechanics to the atom and talk about what's called the Bohr atom, Bohr, as in Niels Bohr. So that's next time.